In the ruins of Pompeii, figures are preserved in their final poses. One person curled on their side, hands covering the face, a family clustered together, a child in an adult's lap. These are not sculptures made by an artist. They are the last moments of people who perished nearly 2,000 years ago, captured in plaster. When excavators dug into the ash that covered the city in 79 AD, they discovered cavities where bodies had once lain. The organic material had decayed over the centuries, but the hardened ash had retained every hollow space. By filling those cavities with plaster, they created casts that show the exact posture each victim took in their final moments: the outstretched arm, the bent knee, the open mouth. It is as close as we can come to a snapshot of a Roman catastrophe, but those plaster casts are only the most visible clue. Beneath the city, under the streets and houses, the eruption left behind something more systematic. Layers of ash and pumice that record the sequence of the event. Each inch of deposit tells a story of what fell from the sky when it fell, and how fast it covered the living city. The ash is a time capsule. It froze not only bodies but also bread in ovens, frescoes on walls, and the very layout of a city that was in the middle of a normal day when the mountain exploded. Yet ash alone does not give the full picture. The bones inside those plaster cavities carry their own evidence. Fractures, charring, and signs of suffocation indicate the cause of fatalities. The position of the skeletons reveals whether people tried to run, hide, or wait, and the walls themselves are a third witness. Some were knocked down by the force of the eruption, others by earthquakes that shook the ground during the event, still others by the weight of debris piling on roofs. The pattern of destruction in a collapsed building can tell a volcanologist whether it was hit by a pyroclastic surge, shaken by a tremor, or simply abandoned and left to decay. So an archaeologist at Pompeii does not just dig up artifacts. They read the ash, the bones, and the broken walls the way a detective reads a crime scene. Each piece of evidence is a fragment of a much larger story, the story of how a disaster unfolded, how people responded, and how a society was wiped out in hours. The ash that sealed, the bones that speak, the walls that fall in patterns only a trained eye can interpret. These three silent witnesses form the foundation of disaster archaeology. How do investigators take these scattered clues and reconstruct something as complex as a volcanic eruption, a tsunami, or an earthquake? How do they tell the difference between a city destroyed by war and one destroyed by nature, or determine whether victims perished from heat, from suffocation, from crushing, or from disease? That is the work of a field that combines volcanology, osteology, architecture, and history to read the physical record of catastrophe. And it begins with the silent witnesses of Pompeii, frozen in plaster but speaking across 2 millennia. The ash, the bones, and the broken walls, each one is a separate kind of silent witness, but no single witness can tell the whole story. The ash might record the chemical fingerprint of an eruption, but it cannot reveal the fate of the people. The bones might show fractures or burning, but they cannot indicate the sequence of building collapse. The walls might lean in directions suggesting an earthquake, but without dating they could be due to centuries of settling. To reconstruct a disaster, archaeologists must coordinate specialists from fields that appear unconnected. Disaster archaeology is not a single discipline but a collaboration among volcanologists who study ash and gas, osteologists who analyze skeletal remains, structural engineers who understand building failure, sedimentologists who read earth layers, and historians who search ancient texts for accounts of the event. Each specialist brings a distinct toolkit and set of questions, and the archaeologist's role is to make sure the pieces fit together. The volcanologist examines the tephra layers left by an eruption like Vesuvius. The thickness, particle size, and direction of each ash and pumice layer record specific moments: the initial fallout, the collapse of the eruption column, the series of pyroclastic surges that swept through the city. This layered timeline gives context to the bones and walls. Without it, those details remain a jumble of tragic fragments. The osteologist studies the skeletons and the cavities that became plaster casts. Bone position reveals posture, whether someone was running, crouching, or lying down. Fractures indicate trauma from falling debris. Burn patterns on bones show exposure to extreme heat. The demographic profile, the proportion of women, children, and elderly among those who perished, reveals which groups were most vulnerable and which had a better chance of escape. But this human dimension depends on already understanding the ash and wall context. The structural engineer or architectural historian examines collapsed buildings to determine the direction of the force that brought them down. Did a wall fall outward or inward? Was it pushed by a blast of superheated gas and rock, or shaken by an earthquake that arrived before the eruption became lethal? The pattern of broken masonry can distinguish between a building knocked over by a pyroclastic surge and one abandoned and collapsed years later. Yet that reading means nothing without the volcanologist's timeline and the osteologist's interpretation of who was inside. None of these specialists works in isolation. The volcanologist needs the osteologist to know whether people perished during an early or late eruption phase. The osteologist needs the volcanologist to distinguish whether bones were altered by heat or by chemical processes in the ash. The engineer needs both to confirm whether the building fell from the eruption or from an unrelated earthquake months earlier. This is detective work at its most intricate, not a single breakthrough but a slow, careful cross-referencing of entirely different kinds of information. One piece of evidence alone, a collapsed wall, a fractured bone, a layer of ash, can be ambiguous, but when the volcanologist, osteologist, and engineer sit down together, contradictions resolve, gaps fill, and the picture sharpens. That interplay of expertise is the real engine of the field, and the first evidence type, the one that usually provides the timeline, is the ash. Ash does not just preserve what it covers. It also records the sequence of the disaster itself, layer by layer, like pages in a book that has not yet been opened. That book opens with the first grains of ash. When a volcano erupts, it does not dump everything at once. The eruption has a sequence, and each phase leaves its own signature in the ground. For Vesuvius in 79 AD, that sequence began with a rain of small white pumice pebbles, light enough to bounce off roofs and accumulate on the streets. Then came denser gray pumice. Finally, after hours of building pressure, the volcano unleashed its most destructive force. That force was a series of pyroclastic surges, avalanches of superheated gas, ash, and rock moving at hundreds of kilometers per hour. What the erupting mountain left behind was not a single blanket of ash but a layered cake, each stratum recording a different moment of the disaster. Because volcanic ash can be surprisingly gentle when it falls dry, it preserved entire moments in the life of the city underneath. The key to reading those layers is a discipline called tephrochronology. Tephra is any fragmented material ejected by a volcano, from dust-sized particles to house-sized blocks. When tephra falls, it lands in order, with thicker layers accumulating near the vent and thinner deposits spreading downwind. More importantly, each eruption has a unique chemical signature, a fingerprint based on the magma's mineral composition. That means a layer of ash found in a trench in Pompeii can be matched to a specific eruption from Vesuvius. It can also be matched to eruptions from other volcanoes, even those thousands of kilometers away. Archaeologists can date a site simply by identifying the ash layer that sits on top of its latest floor. In the same way, a deep core drilled from a lake bed or an ice sheet can preserve layers of ash from eruptions that happened thousands of years before any written record. Each layer is a timestamp, and stacked together they form a chronology that spans millennia. But the real power of ash is not just in dating, it is in what the ash preserves. The same dry, fine material that smothers a landscape can also seal it from oxygen, moisture, and scavengers. At Pompeii, the ash and pumice that fell in the first hours of the eruption did not crush the buildings. Instead, they accumulated gently, filling rooms up to the second story, covering furniture, food, and even the frescoes still glowing on the walls. When archaeologists excavated, they found carbonized loaves of bread still sitting in the stone ovens, their tops stamped with the baker's mark. They found bowls of eggs and fruit that had turned to charcoal but kept their shape. They found graffiti scratched into walls, jokes and insults and election slogans that preserved the voices of ordinary Romans as if they had just stepped out of the room. None of that would have survived without the ash. Normal deposition in soil would have disintegrated the organic material within decades, but the ash acted like a desiccant, drawing out moisture and sealing everything airtight. Then there are the layers that tell the story of the people themselves. The lowest strata, the pumice fall, would have taken hours to accumulate. People had time to flee or to take shelter. But the next layer, the fine white ash that settled later, is where the famous hollow cavities appear. In the final surges, the hot ash hardened around people who were still in mid-motion, forming a cocoon that held their shape even as their soft tissue disappeared. When excavators later poured plaster into the voids, they recovered the exact pose, the clothing, and the final expressions. That stratification, the fact that the body cavities appear only in the upper ash layers, tells us something crucial. The first hours were survivable, but the final pyroclastic surges were not. The eruption had two distinct phases, and the people who perished in the second phase were the ones who had stayed behind, perhaps believing they were safe after the pumice stopped falling. This is where the volcanologist and the osteologist and the structural engineer meet again. The ash layers tell the volcanologist that the eruption had a slow start and a rapid, deadly end. The osteologist sees that the bones in the upper layers show signs of extreme heat, not suffocation. The engineer notes that walls knocked over by the earlier pumice fall fell in a different direction than those toppled by the later surge. The ash is the timeline against which all other evidence is measured. Without it, the rest of the clues would be floating events with no order, no cause, no story. But ash does more than sequence a single disaster. It also ties one eruption to another. The same layer of tephra that covered Pompeii and Herculaneum has been found in sediment cores from the Adriatic Sea and in ice cores from Greenland. That widespread deposit allows volcanologists to pinpoint the exact year of the eruption, not from ancient texts alone but from the ash's position in the global stratigraphic record. In fact, tree ring studies and ice core chemistry have narrowed the date of Vesuvius 79 AD to within a few months. This confirms the Roman historian Pliny the Younger's account that the eruption began on the afternoon of August 24th. A single layer of ash scattered across the northern hemisphere synchronizes written history with geology, and the same method works for eruptions far older. The Minoan eruption of Thura around 1600 BC left a thick layer of white ash on Santorini and across the eastern Mediterranean. That ash layer appears in sediment cores from the Nile Delta, in peat bogs in Ireland, and in ice cores from Greenland. By matching the chemical signature of the Thura ash to these far-flung deposits, researchers have been building a timeline. That timeline links the eruption to climate anomalies recorded in Chinese bamboo annals and to the collapse of the Minoan palaces on Crete. The ash does not just preserve the moment of the disaster, it frames the event, fixes the moment, and carries the evidence across centuries to be read again. The layers are pages, and volcanologists have learned to turn them one at a time. But ash is only one kind of evidence. The story it tells is about timing and context. The human toll, the individuals who lived and died in that frozen moment, that story is written in the bones. Skeletal remains from disaster sites offer a direct record of how individuals perished. Osteologists read that record through trauma analysis, bone chemistry, and demographic profiling. Every fracture, burn mark, and erosion pattern can be interpreted. In Pompeii, many victims found inside buildings show signs of blunt force injuries to the skull, ribs, and limbs. The pattern matches what falling roof tiles and collapsing upper floors would produce during an eruption. Ash and pumice weighed down roofs, and earthquake shocks caused walls to buckle. A person standing in an open courtyard might have taken a direct hit from a falling beam. Someone huddled in a doorway might have been crushed by a collapsing arch. By mapping the positions of fractured bones against the architectural debris found around them, archaeologists reconstruct the exact sequence of structural failure in that room. They can see which walls fell first, which doorways were blocked, and which escape routes were still open when the pyroclastic surge arrived. Heat also leaves evidence. In parts of Pompeii closer to the volcano, bones show calcination. That means they were exposed to temperatures above 700 degrees Celsius, high enough to burn off all organic material, leaving the bone white, brittle, and warped. This is distinct from a house fire. The position of bones relative to the ash layer matters. If a skeleton shows heat damage on the upper side but not the underside, it indicates the person was lying on the ground when the heat pulse hit. If the skull is shattered in a way that suggests steam pressure inside, the cause was heat itself, not suffocation. Body position is another crucial clue. The plaster casts from Pompeii preserve the final posture of victims. Some are curled up, arms over their faces, an instinctive attempt to shield themselves. Others lie flat, as if they simply fell. A few are found in groups, families clinging together. Crucially, some victims are in positions that show they were still moving when they died, with arms outstretched, legs in mid-step, or bodies twisted as if trying to climb over an obstacle. This indicates a sudden event that overwhelmed them within seconds, most likely the pyroclastic surge. Victims of that surge do not have time to adopt a protective posture. They simply collapse in whatever position they were in. Stable isotope analysis reveals diet and origin. Carbon and nitrogen isotopes from collagen in bones or teeth indicate whether a person ate mostly grains, meat, or seafood. Oxygen isotopes from tooth enamel show where they lived as children. Applied to Pompeii victims, these methods reveal a diet rich in seafood and imported goods, suggesting a prosperous town with a diverse population. DNA work has confirmed family relationships. In the Garden of the Fugitives, a group of 13 victims huddled at the base of a wall. Genetic analysis showed that several individuals were closely related, confirming historical accounts that families died together. Demographic profiling identifies who was most vulnerable. Examining age and sex across the city, archaeologists see that young children and elderly adults are underrepresented among the escaped remains, consistent with slower evacuation. Strikingly, during the early phases of the eruption, when the city was still being evacuated, the victims are mostly men, matching Pliny the Younger's account of rescue efforts. Later, as the eruption intensified, the victim profile shifts to include women, children, and the elderly who did not manage to leave. This reflects the social dynamics of a disaster, not a random distribution. Systematically studying hundreds of individuals, mapping their positions, recording their traumas, and analyzing their chemistry turns a statistical event into individual stories. In Pompeii, those stories coalesce into a concrete discovery. The distribution of victims across the city, combined with their trauma patterns, shows that the death toll was not a single event but a series of waves. The first wave during the pumice fall killed mostly those who were slow or unlucky. The second wave, the pyroclastic surges, killed everyone still inside. The final surge that buried the city killed anyone who had survived the earlier ones. That sequence, read from broken bones and preserved postures, matches exactly what volcanology now knows about the eruption's behavior. The two lines of evidence, ash and bone, converge on the same story. Beyond ash and bone, there is a third witness, the walls themselves. Buildings carry their own language of force. Cracking, tilting, shearing, and collapsing in particular directions form a fingerprint of the energy that struck them. Reading that fingerprint is how archaeologists distinguish an earthquake from a tsunami, a fire, or deliberate human destruction. Start with earthquake damage. When the ground shakes, buildings do not fall randomly. They fail in predictable ways. Walls shear along diagonal lines, especially near openings like doors and windows. Columns topple in a consistent orientation aligned with the direction of the seismic waves. Entire floors tilt, preserving a frozen lean that no other disaster creates. Crucially, collapsed debris spreads horizontally in a wide, low pile because the building pancaked downward rather than being blown outward or swept aside. Archaeologists excavating a site map these details. They record the angle of a fallen column, the direction of wall cracks, and the spread of rubble. From these, they deduce not only that an earthquake happened, but sometimes the approximate epicenter and magnitude. The pattern is consistent enough that a single collapsed building is suggestive. But when dozens of structures across a city show the same orientation, it becomes a diagnosis. Now contrast that with a tsunami. Water moves differently. It does not shake, it sweeps, scours, and deposits. Tsunami damage in the archaeological record looks like a giant broom passing through a city. Debris piles up against the landward side of walls, not scattered evenly. Boulders and heavy objects are displaced inland from the coast, often carried tens or hundreds of meters. The sediment itself is distinctive, poorly sorted sand and gravel, sometimes layered with marine shells deposited inside buildings. There is a characteristic scouring at the base of walls where the turbulent water excavated the ground. In some cases, entire structures are removed, leaving only their foundations while adjacent buildings survive because they were slightly higher or better protected. Tsunamis do not discriminate by structural strength in the same way earthquakes do. A reinforced building might stand against shaking but be stripped bare by a wave. Fire leaves its own signature. The most telling sign is vitrification. When stone or brick is heated to extreme temperatures, its surface melts and turns glassy. Ash and charcoal layers accumulate inside rooms, not just outside. Because fire spreads upward and outward, damage is often concentrated on the upper floors or the leeward side of a building relative to the wind. In a city that burned, you might find collapsed roofs with their timber supports completely carbonized while the lower walls remain intact. The heat also fractures stone in a way that looks different from impact or shaking. There is more spalling and cracking along natural grain boundaries. Fire damage can mimic earthquake collapse if the flames weaken a structure enough to bring it down. But the presence of vitrified surfaces and concentrated ash deposits reveals the true cause. Of course, these signatures can overlap. A building struck by a tsunami may also burn if the wave knocked over lamps. An earthquake can ignite fires. Part of the detective work is teasing apart which came first and which did the most damage. There is a further complication. Human destruction, intentional demolition, siege equipment, fire set by an invading army, leaves marks that can mimic natural disasters. That ambiguity will surface later. For now, the point is that each type of force has a preferred set of scars. When those scars are consistent across dozens of buildings in the same city, they become a diagnosis. One of the clearest examples of reading broken walls comes from the Mediterranean island of Crete. In the summer of 365 CE, a massive earthquake struck near the southwestern coast. It was so powerful that it lifted parts of the island by as much as 9 meters, permanently changing the coastline. The archaeological record of that event is unmistakable. Across multiple sites, from the Roman city of Gortyn to the coastal settlement of Phalasana, buildings display identical patterns. Nearly all walls collapsed to the southeast. Columns fell in parallel orientations. There is no evidence of fire or water damage. The consistency points to a single seismic event, not a series of separate tremors. The directionality tells modern seismologists that the fault ruptured offshore southwest of Crete, generating waves that would have hit the Egyptian coast about half an hour later. But the concrete discovery is not just that the earthquake happened. It is what the broken walls reveal about the scale of the disaster. At Gortyn, the Roman capital of the province, entire public buildings were reduced to rubble and never rebuilt. The forum collapsed, the temple structures were abandoned. Excavations show that the city was not immediately reoccupied in the same way. The population contracted and the urban plan shifted. That is a physical echo of the social and economic disruption that ancient historians described. Ammianus Marcellinus wrote that the sea withdrew from the shore and then returned with such force that it drowned thousands of ships and thousands of people. The broken walls give a ground truth. They offer a way to measure the earthquake's actual intensity, independent of the written accounts. They show that in Crete, the 4th century disaster was not just a momentary tremor but a turning point in the region's history. It redrew the map of a civilization, but not every ancient disaster leaves its signature in collapsed walls. When the disaster is a volcanic eruption, the evidence takes a very different form, and even within the same catastrophic event, the way people perished can vary dramatically depending on exactly where they were. That is the lesson of Herculaneum, a Roman town only a few kilometers from Pompeii along the same Bay of Naples, that met an entirely different fate during the same eruption of Mount Vesuvius in 79 CE. For nearly 2 centuries after the rediscovery of Pompeii, Herculaneum seemed to tell a different story. Excavators found the town buried under a much thicker layer of volcanic material, up to 20 meters deep in places, but they found very few human remains. They assumed that most residents had escaped. Then in the 1980s, a team digging along the ancient shoreline made a significant discovery. In a series of stone chambers that had once been boat sheds, they found more than 300 skeletons. This was not a small group caught by surprise. It was the majority of the population, huddled together in the only shelter they could find. The condition of those skeletons was immediately unusual. They were not lying in the ash in the positions of sleep or struggle seen at Pompeii. Many were contorted, with limbs pulled inward as if the muscles had contracted violently at the fatal moment. Some skulls had fractured open. The bones were not the chalky white of ordinary archaeological remains. They were brittle, discolored, and in some places almost glassy. Forensic analysis soon clarified what had happened. The heat of the first pyroclastic surge that hit Herculaneum was far greater than anything that reached Pompeii. Temperatures in that initial wave reached at least 500 degrees Celsius, perhaps as high as 700. The soft tissue of the body vaporized almost instantly. Blood in the veins boiled, and the brain inside the skull expanded so rapidly that the bone cracked from the pressure. That violent expansion of bodily fluids caused the muscle contractions that left the skeletons in those twisted, defensive poses. This is why no plaster casts exist from Herculaneum. In Pompeii, the ash fell as a fine, slow rain that buried victims gradually. Their soft tissue decayed over days and weeks, leaving cavities in the hardened ash that could later be filled with plaster. In Herculaneum, the soft tissue did not decay. It evaporated in an instant. The bones were left exposed, but the space where flesh had been collapsed around them. There was no cavity to preserve the shape of the body. What survived was the skeleton itself, but a skeleton that carried the thermal signature of a death beyond anything the human body was designed to survive. The difference between the two towns is not just a footnote. It changes the entire narrative of the eruption. For decades, volcanologists believed that the first lethal phase of the Vesuvius eruption was the falling pumice and ash that buried Pompeii. But the Herculaneum skeletons show that the real killer came earlier and was far more extreme. A pyroclastic surge, a ground-hugging cloud of superheated gas and ash, raced down the mountain and hit Herculaneum about an hour before the ash column collapsed over Pompeii. The people in the boat sheds never had a chance. They did not suffocate. They did not slowly lose consciousness as ash filled their lungs. They were subjected to extreme heat that ended their lives almost instantaneously. The concrete discovery from Herculaneum is that the same disaster took two completely different forms within a few kilometers. One community succumbed to heat. The other succumbed to asphyxiation. And the archaeological evidence, the bones versus the cavities, tells researchers not just how these people died, but exactly when during the sequence of the eruption the fatal moment came for each community. That timing has reshaped the modern understanding of Vesuvius and the risk it poses to Naples today, because it shows that the first surge can arrive without warning, faster than the ash fall, and with temperatures that leave nothing but charred bone behind. The Herculaneum skeletons forced volcanologists to revise their models of eruption dynamics, recognizing that pyroclastic surges can precede the main ash column and strike with devastating speed. This knowledge directly informs evacuation planning for the 3 million people living in the shadow of Vesuvius today. The bones from the boat sheds are not just evidence of an ancient tragedy. They are a practical warning about the unpredictable nature of volcanic hazards, one that continues to influence how scientists assess risk and prepare for future eruptions. The Mediterranean holds an older eruption that may have brought down an entire civilization. Around 1600 BC, on the island of Thura, modern Santorini, a volcano erupted with far greater force than Vesuvius. The Minoan town of Akrotiri was a prosperous Bronze Age trading hub with multi-story buildings, advanced drainage, and vivid frescoes still on the walls. When excavators uncovered the site, they found the structures preserved under layers of pumice and ash, much like Pompeii. The walls stood tall, the frescoes remained intact, and storage jars still held their contents. But there was a critical difference. Almost no human remains were found. Where Pompeii yielded hundreds of cavities and skeletons, Akrotiri yielded just a handful. The people had escaped. The evacuation left the town intact but empty, and that absence became the first major clue about the nature of this eruption. The ash and pumice layers preserved the architectural layout with remarkable clarity. Excavators could read the eruption sequence in the deposits themselves. The lowest layer was fine white ash from an initial explosive phase that sent a column of ash and pumice into the atmosphere. Above that, thicker pumice showed the eruption intensifying, burying the town under meters of material. Buildings collapsed under the weight, but the pumice also protected the lower floors, sealing them from erosion and decay. Preservation was so good that wooden furniture, food remains, and even the outlines of woven textiles survived. But the absence of bodies told archaeologists something crucial. The eruption gave warning. People had time to leave before the worst phase hit, and they took their valuables with them. Few precious objects were found compared to what a thriving town would normally contain. The Thura eruption was not a sudden pyroclastic surge that caught everyone by surprise. It was a prolonged event with clear precursors that allowed an organized evacuation. That evidence changed how volcanologists understand large eruptions. The pumice and ash layers at Akrotiri are not just a record of destruction. They are a time sequence of warning signs that the ancient inhabitants recognized and acted upon. The disaster did not end at Thura. The eruption generated massive tsunamis, and those waves carried destruction much farther than the ash cloud. On the northern coast of Crete, about 100 kilometers south, archaeologists have found layers of marine sediment, pumice, and broken pottery dating to the same period. These tsunami deposits lie inside coastal buildings and extend inland for several hundred meters, indicating waves at least 10 meters high swept across Minoan settlements. Excavations at sites like Palecastro and Amnisos show collapsed walls, displaced stone blocks, and debris matching a tsunami signature rather than earthquake or fire. The Minoan civilization was the dominant power in the Aegean, with palaces, ports, and trade routes. The tsunami would have devastated coastal infrastructure, destroyed fleets, and disrupted agriculture by salting fields with seawater. Archaeological evidence from Crete shows a clear disruption in occupation at many coastal sites around the time of the eruption. Some were abandoned for decades. Others were rebuilt on a smaller scale. The question that still divides researchers is whether this disaster was the primary cause of the Minoan decline or just one factor among many. Thura erupted during a period already experiencing social and political stress across the eastern Mediterranean. There is evidence of internal unrest, shifting trade patterns, and the rise of competing powers on the Greek mainland. The tsunami damage on Crete was severe but not total. Palaces in the interior, like Knossos, show no direct signs of tsunami impact and continued to function for another century or two. So the role of the eruption remains an open question, one that archaeologists continue to debate with fresh evidence from sediment cores, radiocarbon dating, and underwater surveys. What makes Thura so valuable for disaster archaeology is the direct contrast with Pompeii and Herculaneum. In those Roman towns, the victims were trapped, and the evidence records their final moments. The bones and cavities tell a story of failed escape. At Thura, the absence of bodies tells a story of successful evacuation. The buildings are not filled with the remains of people who ran too late. Instead, they are filled with everyday objects a community decided to leave behind. The frescoes, storage jars, and furniture are not evidence of a civilization frozen in its final moments. They are evidence of one that had enough warning to save its people. That difference has profound implications for interpreting disaster sites. When you find bodies, you know the disaster was fast and lethal. When you do not find bodies, you have to ask whether the inhabitants escaped or whether the remains simply did not survive. At Thura, the lack of human remains combined with the orderly abandonment of valuables points strongly to evacuation. But at other sites, the absence of bodies can be ambiguous. Fire, decay, or later disturbance can remove remains entirely, leaving archaeologists to wonder whether the people died elsewhere or survived. Thura provides a clear example of how to interpret the absence of evidence as a clue in itself. Thura also raises the stakes beyond a single town. Pompeii and Herculaneum were regional disasters that destroyed two small Roman communities. Thura was a regional catastrophe that affected an entire civilization. The ash cloud disrupted climate patterns across the northern hemisphere. The tsunamis struck multiple coastlines. The economic and social disruption may have contributed to the end of the Minoan Bronze Age, one of the first great civilizations of Europe. The archaeological evidence from Thura and Crete does not give a simple answer to the question of Minoan collapse, but it does give researchers a precise chronological marker. The tephra from Thura has been found in ice cores from Greenland and in sediment layers across the Mediterranean, allowing scientists to date the eruption with increasing accuracy. But even here there is debate. Radiocarbon dates from Akrotiri yield a range between 1600 and 1500 BC, while ice core data points toward a slightly later date around 1560 BC. The gap is small in human terms but significant for correlating events across the ancient world. This ongoing push to refine the date of Thura is one of the most active areas of research in disaster archaeology because the exact timing determines how the eruption fits into the larger history of the Bronze Age Mediterranean. It connects volcanology, archaeology, and climate science in a single investigation, and it shows that even the most basic fact about a disaster, the year it happened, can remain uncertain when reading the evidence from ash, bones, and broken walls. That same uncertainty applies even more sharply to earthquakes. Unlike a volcanic eruption that leaves a layer of ash, an earthquake deposits no distinctive blanket. Its signature is written entirely in broken walls and collapsed structures, but many things can break walls and collapse columns. Poor masonry, gradual decay, deliberate demolition, even a violent storm. So how do archaeologists tell the difference? This is the work of archaeoseismology, which treats collapsed buildings as diagnostic evidence. The key is not a single damaged wall, but the pattern of damage across an entire site. When an earthquake strikes, the ground moves in a specific direction, and that motion leaves a directional fingerprint. Archaeologists look for walls that have fallen in the same orientation, columns that lean at the same angle, and floors that show a consistent slope. Random destruction suggests decay or human action. Systematic destruction points toward a seismic event. One vivid example comes from the Roman city of Curion on Cyprus. In 365 AD, a massive earthquake struck the eastern Mediterranean. At Curion, buildings collapsed exactly as they stood. Walls had sheared along fault lines, with entire facades toppling in the same direction. Inside, archaeologists found skeletons in sleeping poses with oil lamps still beside them. Coins lay on nightstands and cooking vessels remained in the hearths. The city was never rebuilt. That abandonment itself is a clue. When an earthquake is severe enough to make survivors leave a place permanently, it leaves a clear archaeological horizon. Radiocarbon dating of charcoal from the destruction layer, combined with coins and pottery from the mid-4th century, placed the event in 365 AD. Because the victims were found in sleeping poses with their lamps still beside them, archaeologists concluded that the earthquake struck at night. That detail changes how we imagine the disaster. Not a daytime threat that people could see coming, but a sudden awakening in the dark. Curion is a textbook case, but not every earthquake is so easy to identify. Sometimes evidence is ambiguous because of pseudo-seismic effects. A poorly built wall can collapse under its own weight and look identical to an earthquake collapse. In Pompeii, for example, there is clear evidence of an earthquake that struck 17 years before Vesuvius erupted. The 62 AD earthquake damaged many buildings, and repairs were still underway when the ash fell. But if historians had not recorded that earthquake, could archaeologists identify it from structural damage alone? Possibly, but only with caution. The key is to look for multiple criteria. Aligned damage across the city, evidence of sudden abandonment, and destruction that cannot be explained by settlement or rot. At Pompeii, the damaged walls show a consistent pattern of tilting toward the southeast, matching the direction of seismic waves from the epicenter near Nuceria. By mapping the damage distribution across the region, archaeologists can reconstruct the earthquake's magnitude and approximate its epicenter. This process resembles how modern seismologists create isoseismal maps, but instead of instrumental readings, archaeologists use the angle of fallen columns, displacement of foundations, and skeletal fractures consistent with falling masonry. When such fractures appear in many skeletons within the same destruction layer, and when the damage pattern is consistent across multiple structures, the case for an ancient earthquake becomes strong. A more ambiguous example comes from the Bronze Age city of Ugarit in modern Syria. The city was destroyed around 1180 BC, and its ruins show a clear pattern of collapsed walls and fallen masonry aligned in a single direction. The destruction layer also contains tablets describing what appears to be a series of tremors, but the debate continues. Was Ugarit destroyed by an earthquake or by the so-called sea peoples who were raiding the coast at that time? The archaeological evidence alone cannot settle the question. That ambiguity is what makes archaeoseismology so challenging. A single collapse might look seismic, but when the human record includes invasions, fires, and economic collapse, the earthquake hypothesis must compete with other explanations. Despite these challenges, there are cases where archaeologists have successfully inferred magnitude and epicenter. The 365 AD earthquake that destroyed Kourion also devastated much of the eastern Mediterranean. On Crete, the same earthquake lifted the coastline by several meters, creating raised beaches still visible today. Combining the structural damage across dozens of sites with the geological evidence of coastal uplift, researchers estimated a magnitude of at least 8.0. That is a single archaeological layer, read through broken walls and tilted floors, telling us not only that a disaster happened but how powerful it was and where it began. Earthquakes leave a signature that is both precise and ambiguous. They are precise when the damage is systematic, abandonment is sudden, and dating is tight. They are ambiguous when evidence is sparse or multiple forces could have acted on the ruins. But even the ambiguity is useful. It forces archaeologists to sharpen their criteria, look for multiple lines of evidence, and accept that some questions may remain open. At Kourion, they found skeletons with their lamps still burning. That image is a kind of time stamp telling us that the earthquake struck at night, that people died in their homes while they slept, and that the disaster was so complete that the city was never reoccupied. From broken walls and scattered bones, archaeologists reconstructed not just the fact of the earthquake but the moment it hit. A major earthquake can also displace seawater, generating a tsunami. That wave leaves a distinct deposit inland. Archaeologists searching for ancient tsunamis look for a layer of sand where there should be soil, marine shells far from the coast, and broken pottery mixed with pebbles from the seafloor. This is the signature of a powerful inundation that carries ocean material inland and drops it as the water recedes. Unlike the slow burial by ash or the single collapse of an earthquake, a tsunami deposits a chaotic mix of sediment, often wedge-shaped and thinning inland. The layer may be graded, with heavier pebbles at the bottom and finer sand at the top, because the wave slows as it moves across land. A trench through a coastal site that reveals broken amphora fragments alongside crushed seashells and bits of coral points to a tsunami event. Distinguishing this from a storm surge requires more than sediment alone. Storm surges are driven by wind and tend to erode the coast rather than deposit. Tsunami waves have much longer wavelengths and can carry heavy objects inland for kilometers. They also leave distinctive damage on structures. When a tsunami hits a building, the water pushes from a consistent direction, leaving scour marks around foundations and sometimes tilting the structure in the flow direction. Archaeologists have found walls with horizontal striations, water lines that mark the flood height. Heavy stone blocks weighing several tons are displaced not by random wave action but systematically pushed in one direction. In the ancient harbor of Alexandria, columns and statues toppled in a uniform orientation toward the sea. That seems counterintuitive, but the return flow, the backwash, is equally powerful. Debris is often scattered in two phases, first inward, then outward. Historical accounts provide another verification layer. The 365 AD earthquake that devastated Crete was followed by a tsunami that struck coastal towns across the Mediterranean. The Roman historian Ammianus Marcellinus described ships carried onto rooftops and then washed back out. For a long time, those accounts were considered exaggerated. Then archaeologists found physical proof. One of the most revealing case studies comes from ancient Olympia, home of the Olympic Games. Olympia lies about 7 kilometers inland from the Ionian Sea. For decades, excavators noticed an unusual layer of sand and marine shells in the sanctuary's stratigraphy, in the floor of the gymnasium, the stadium, and around the Temple of Zeus. In the 1990s, a team of geologists and archaeologists analyzed that layer. They found a deposit up to 2 meters thick, containing deep-water microfossils, fragments of mollusks, and bits of pumice. The layer was not a river flood or a storm. There was no estuary nearby, and the sediment did not match local geology. It was marine sand carried inland and dumped in a single powerful event. Radiocarbon dating placed the deposit in the 6th century AD, matching the 365 AD earthquake and tsunami. The wave must have been at least 10 meters high when it hit the coast, surging inland across the low-lying plain, carrying sand, shells, and debris all the way to Olympia. The sanctuary was covered in sediment up to the stadium embankments. The event altered the landscape, silting up the river mouth and changing the course of the Alpheus River. Olympia never fully recovered. The games continued for a time, but the area became marshier, and the sanctuary was eventually abandoned. This discovery changed how historians understood the 365 AD disaster. It was not just an earthquake that destroyed a few cities. It was a multi-hazard event, a massive quake, a tsunami, and a long-term environmental transformation that reshaped the coastline of the Western Peloponnese. The evidence was not a single broken wall or a pile of bones. It was a layer of sand and shells, invisible to the untrained eye, that told the story of a wave that rewrote the geography of an ancient landscape. Identifying ancient tsunamis is not always straightforward. Overwash layers are often eroded or disturbed by later human activity. A site that was reoccupied may have its tsunami deposit mixed with building debris. Storm surges can mimic a tsunami, but the sediment characteristics differ. Tsunami deposits are generally finer at the base and coarser at the top, the reverse of a storm deposit. When the archaeological context is right, the evidence is unmistakable. At Olympia, the marine sand layer was found directly on top of Roman-era floors, with no gradual accumulation. It was a sudden interruption followed by centuries of silence. That is the power of sediment as a witness. It does not decay like organic matter, nor does it narrate like a text. But read correctly, a layer of sand can reveal the height of a wave, the direction it came from, and the moment it struck. It can show that a famous earthquake also unleashed a wave that traveled hundreds of kilometers and changed the course of history for communities that never saw the fault break. From broken shells and misplaced pebbles, archaeologists reconstruct not just the event, but the scale of the disaster that followed. Water does not leave only sand and shells. Sometimes it leaves nothing at all, and the evidence of disaster comes instead from heat. Fire is common in the archaeological record, but hard to interpret. A thick layer of charcoal and ash might represent the final moments of a building, but was it an accident, an act of warfare, or a ritual cleansing? Archaeologists read the burn layer like a forensic investigator reads a modern scene. The most obvious signature is charcoal. Wood, thatch, and textiles leave carbonized remains that can survive for millennia, but charcoal alone does not tell much. It could come from a hearth or a deliberate conflagration. To extract detail, archaeologists turn to materials that change under extreme heat. Pottery deforms or melts above about 1,000 degrees Celsius. Glass melts at a similar range. When excavators find a collapsed wall with glass that has flowed and resolidified, they know the temperature exceeded that material's melting point. Such heat comes from a fully developed structure fire or a citywide blaze. Vitrification, the transformation of clay or stone into a glassy surface, is another clue. Walls vitrified on one side but not the other indicate the fire's direction and intensity. Skeletal material also records temperature. Bone color and shrinkage change at known temperatures, allowing osteologists to estimate how long the fire lasted and its intensity. The most well-known ancient urban fire is the Great Fire of Rome in AD 64. Historical accounts from Tacitus describe the fire sweeping through the city for 6 days, destroying 3 of 14 districts and severely damaging 7 more. But historical accounts are biased. The archaeological evidence offers a cross-check. Excavations along the Via dei Fori Imperii uncovered a clear destruction layer dating to Nero's reign. The layer is a band of blackened debris up to half a meter thick, filled with charred wood, burned pottery, and melted glass. The distribution matches the reported path of the fire. The southern slopes of the Palatine Hill show intense burning, while areas to the north escaped nearly untouched. By mapping smoke and scorch patterns on surviving walls, archaeologists have reconstructed the fire's movement through the Roman Forum. The evidence shows that the fire burned hottest at the base of the Palatine, precisely where the emperor's palace stood, which has fueled debate about whether the fire was intentional. To distinguish accidental fire from deliberate arson, archaeologists look for multiple ignition points. A single origin produces radiating damage. Separate simultaneous burn centers suggest human action. For the Great Fire of Rome, some ancient sources accused Nero of ordering the fire to clear land for his Domus Aurea. The archaeological evidence does not prove or disprove that claim. It does show that the fire started in the Circus Maximus area, not near the Palatine. Many shops had their wooden roofs partially burned before the main fire arrived, indicating advance heat from windborne embers. The physical evidence supports a natural spread fueled by Rome's narrow streets and wooden tenements, not a coordinated plot, yet the impact was the same. The destruction layer is so thick and uniform that it represents a single catastrophic event, not a series of small fires. Beyond temperature and distribution, fire layers contain microremains that reveal what burned. Flotation of ash samples recovers charred seeds, pollen, and insect remains. At Rome, the ash layer from AD 64 contained grains of wheat, lentils, and figs, the contents of storehouses and shops. These remains show not just that the fire happened, but that it caught the city during its ordinary daily life, with food supplies still in place. No gradual evacuation, no systematic salvage. People fled and their possessions burned. One of the most valuable discoveries from fire evidence is precise dating. Charcoal from burned wood can be radiocarbon dated, but that gives a range of decades. When the fire layer contains coins or pottery that can be dated more tightly, the moment of destruction becomes a pin in the timeline. The Great Fire of Rome layer includes coins of Nero minted between AD 62 and 64, narrowing the fire to the winter of AD 64, exactly when the historical sources place it. The convergence of physical and textual evidence makes this one of the best documented ancient disasters. But not every fire layer represents a disaster. In many settlements, fires were a routine hazard. A single building might burn and be rebuilt within a generation. The key to distinguishing a catastrophic fire from a routine one lies in spatial extent and the absence of cleanup. A disaster fire leaves a widespread, unconsolidated layer of debris that was not removed before rebuilding. Collapsed walls lie exactly where they fell, with ash and charcoal sandwiched between the floor and the new surface above. That shows the occupants did not have time or resources to clear the damage. In contrast, a localized fire often shows evidence of cleanup, burnt material removed, new foundations cut through the old debris. The Great Fire of Rome left a layer of debris that was sealed by massive rebuilding projects. Nero used the disaster to impose a new urban plan with wider streets and fire-resistant materials. The burn layer became a dividing line in Rome's archaeological sequence. Everything below it belonged to the old city of narrow alleys and wooden apartments. Above it, stone masonry and concrete vaults rose. The fire layer itself, with its warped glass and carbonized grain, is the boundary between two versions of the same city. That concrete discovery shows how archaeologists read fire not only as destruction but as a catalyst. A single fire layer can mark a transformation in urban architecture and planning. The evidence is fragile. Charcoal crumbles, glass reliquefies under later heat, and ash washes away. But when it survives, a fire layer captures a moment when the temperature of a city spiked and everything changed. It is the signature of a disaster that carries its own heat source. The difference between a cooking fire and a city-killing conflagration is written in the colors of the bones and the curves of the melted glass. Not all disasters leave a visible scar of fire. Epidemics kill invisibly, and the evidence is not in melted glass but in how the dead were buried. There is no chemical marker in ash, no directional collapse to map. The signature of a plague is human behavior, digging a pit and throwing in the dead without ceremony because the living are too sick or too afraid to do anything else. When archaeologists find a mass grave, the first clue is context. A typical cemetery has orderly rows of individual graves, each aligned and often with grave goods. A plague pit is a hole in unconsecrated ground outside the city walls, bodies stacked without coffins, often stripped of clothing. The layers tell a story of haste. On top, the last victims are carelessly placed, suggesting survivors were barely functioning. One of the most famous examples comes from London, excavated in the 1980s during construction at the Royal Mint site, just outside the old city walls. The digging machines hit a layer of dark soil filled with human bones. The site became one of the largest archaeological investigations of a plague cemetery in Europe. It was part of the East Smithfield burial ground, established in 1348 at the start of the Black Death. Historical records described a massive pit dug to take bodies from nearby parishes, as many as 200 a day at the peak. Archaeologists faced a difficult task. Bodies were tightly packed in layers, soil conditions changed over 6 centuries. Each skeleton had to be lifted, cleaned, and analyzed. What they found was a demographic snapshot of a city in crisis. Skeletons showed no signs of trauma, no cuts or fractures, but the age distribution was striking. The Black Death killed across all ages but disproportionately struck young adults between 18 and 40 years old, the people who worked, traded, and raised children. In a normal medieval cemetery, you see a balanced age curve with higher infant mortality and gradual decline into old age. The plague pit looks like an army of young adults was cut down. But age was only part of the story. Bones held molecular evidence. In the early 2000s, a team extracted DNA from the teeth of several skeletons in the East Smithfield pit. Teeth are ideal for ancient DNA because enamel protects the pulp cavity. Inside the pulp, blood-borne bacteria can be preserved. The team found DNA fragments of Yersinia pestis, the bacterium that causes bubonic plague. That confirmed beyond reasonable doubt that the Black Death was indeed a plague pandemic. Geneticists reconstructed the ancient bacterium's genome and compared it to modern strains. The medieval strain had the same virulence factors as modern plague. The difference was not the microbe but the host population, with no immunity and no knowledge of germ theory. Demographic analysis went further. By measuring nitrogen and carbon isotopes in the bones, researchers reconstructed diet. Plague victims had eaten a typical medieval diet of grains and some meat. But survivors in subsequent generations showed a different isotopic signature, higher nitrogen levels, meaning more protein from better access to meat. That suggests the plague culled those whose nutrition was compromised. The survivors were the better fed, who may have had stronger immune systems. Nutritional status remains a key predictor of survival in modern epidemics. The grave itself tells a social story. In medieval England, a proper burial meant a consecrated grave, an east-west orientation, and often a shroud. Plague victims had none of that. They were buried in mass pits, sometimes with lime to speed decomposition. The lack of grave goods, no jewelry, no coins, no religious tokens, is not because items were lost. Bodies were handled as quickly as possible. The community had to choose between the dead and the living. They chose the living. That decision is written in the dirt. The London Plague Pit is not alone. Similar mass graves have been found across Europe, from Paris to Vienna to Venice. Each excavation adds a data point. By combining archaeology with historical records of parish registers and civic accounts, researchers estimate mortality rates. The East Smithfield burial ground alone may have held as many as 400 bodies, a tiny fraction of the estimated 50,000 Londoners who died in 1348 and 1349. Multiply that across the continent and the scale of the catastrophe becomes clear. This is where contemporary relevance comes into focus. Studying plague pits is not just historical curiosity. It provides a baseline for how pandemics behave in pre-modern populations. Patterns of transmission, the role of immunity, social factors that determine who lives and who dies apply directly to modern outbreaks. When COVID-19 struck, epidemiologists looked back at the Black Death. The demographic profile of severe illness in the modern pandemic, older adults and those with underlying conditions, echoed vulnerability patterns seen in medieval plague pits. The medieval disease also killed the young and robust, but the underlying lesson is the same. Pandemics exploit inequality. The poor, the malnourished, the densely housed die first. Archaeology cannot stop a pandemic, but it shows how past societies broke under the weight of disease and how they rebuilt. Mass graves are monuments to a collapse in the social contract. When the living could no longer bury the dead properly, society was stretched to its limit. Yet Europe survived, cities recovered, trade resumed. That resilience is also written in the ground, in the orderly graves that appear after the plague crisis passed. The chaos of the mass pit is followed by a return to normal burial practices. The dead are once again treated with respect. Studying epidemics through archaeology reveals not only the disaster but the capacity for recovery. The bones and pits are not just evidence of death. They are evidence of endurance, but not every destruction layer has a natural cause. Some of the most dramatic archaeological records of collapsed cities were written not by eruptions, earthquakes, or disease, but by human hands. War leaves its own signature in the ground, and telling the difference between a city destroyed by nature and one sacked by an army is one of the hardest puzzles disaster archaeologists face. The clues are subtle but distinct. Start with the walls. In an earthquake, buildings tend to fall in a consistent direction. Walls shear along fault lines or topple in parallel rows. In a siege, the damage is more chaotic. Breaches cluster at gates and weak points. Arrowheads and sling stones litter the ground just inside the walls, concentrated where defenders would have stood. The destruction layer itself might be thicker in some areas and thin in others. It looks patchy, as if the fire spread unevenly from one building to the next rather than sweeping across the entire city in a single shock. Then there are the human remains. In natural disasters, remains often lie where people fell, scattered across a site without clear organization. But in a deliberate destruction, remains frequently appear in mass graves outside the city walls. These pits sometimes show signs of organized killing, such as bound hands or blunt force marks on the skull. Multiple individuals may be stacked without grave goods. Inside the city, remains are found in defensive positions, huddled near doorways or collapsed behind barricades. the distribution tells a story of organized conflict, not random catastrophe. One of the most famous and contested examples is the destruction of Carthage in 146 BC. According to Roman accounts, after a 3-year siege, the city was systematically burned and its buildings razed. The surviving population was sold into slavery, and legend claims the Romans sowed the fields with salt to ensure nothing would grow again. Archaeology has confirmed parts of the story. Excavations at the site of Carthage in modern Tunisia reveal a thick destruction layer dating to the late 2nd century BC, packed with charred debris, collapsed walls, and the remains of hastily abandoned homes. But the salt story, no trace of soil salinization has been found. That part appears to be a later embellishment. What the ground does show is a very specific pattern of burning, concentrated along the main streets and near the waterfront, consistent with a coordinated military demolition rather than a random fire. But here is where the detective work gets slippery. A destruction layer that looks like a siege could also be the result of an earthquake that triggered a fire, followed by survivors abandoning the site. How do you tell them apart? The answer often lies in the small details. Arrowheads and sling stones are not ambiguous. If you find dozens embedded in the walls of a single house, that is not a tremor. It is a fight. Similarly, remains with cut marks on bones from swords or axes are clear evidence of interpersonal conflict. But what about a site where no weapons are found, yet the destruction is total? That is when archaeologists turn to historical texts. If a written record mentions a sack at a specific date, and the radiocarbon dates from the destruction layer line up, the case is strong. But if the texts are silent or contradictory, the ambiguity remains. Sometimes the human disaster is indistinguishable from a natural one, at least at first glance. The Roman siege of Masada in 73 AD left a clear picture. The ramp, the camps, the weapons, the collective decision of the defenders to end their own lives. But for every Masada, there is a site like the burned town of Tel el-Hesi in the Levant, where archaeologists have debated for decades whether the destruction was caused by an invading army or an accidental fire that got out of control. The evidence points both ways, and without a decisive clue, the question stays open. This is where disaster archaeology meets a deeper philosophical problem. The same pattern of broken walls, scattered remains, and ash can be produced by very different causes. A volcanic eruption, a plague, an earthquake, a tsunami, a fire, a siege, a sack. Each leaves a signature, but those signatures can overlap. How do you know you are reading the evidence correctly? How do you distinguish a city that fell to an earthquake from one that fell to an army? That ambiguity is not a weakness of the method. It is the central challenge that makes the field so intriguing. And confronting that ambiguity is where the real science begins. That ambiguity has a name: equifinality, the principle that different causes can produce nearly identical physical evidence. A single destruction layer of collapsed walls, ash, and broken pottery could be an earthquake, a fire, a tsunami, or a military attack. The material remains look the same. The question is not whether the layer exists but what created it, and answering that requires more than a single clue. Archaeologists deal with equifinality by combining multiple independent lines of evidence. This is the multi-proxy approach. The composition of the ash, the orientation of collapsed material, the condition of skeletal remains, the stratigraphic relationships, radiocarbon dates, and any contemporary texts all become part of a converging argument. Each piece narrows the range of possible causes until only the most likely remains. Consider the destruction layers at Troy. The ancient city was rebuilt many times, and each layer tells a different story. In the late 19th century, Heinrich Schliemann identified a thick destruction horizon and assumed it was the Troy of the Trojan War described in the Iliad. He found evidence of fire, fallen walls, and human remains and declared it a war destruction. Later excavators looked more carefully. Troy VI, the layer from around 1300 BCE, had walls that were not just burned but shifted and tilted in a way that suggested seismic shaking. The masonry showed shearing and rotation typical of earthquakes. Pottery on the floors was in place, not broken by looters. Few human remains were found, which fits a sudden natural event where residents could escape. The fire that followed may have come from overturned lamps and braziers, not enemy torches. Today the consensus is that Troy VI was destroyed by an earthquake, not war. The destruction Schliemann attributed to the Trojan War was actually Troy VI, a slightly later layer burned and sacked by human forces. The difference was only visible after careful analysis of structural damage, fine distribution, and collapse patterns. The Troy debate shows how equifinality forces archaeological method. Without the multi-proxy approach, the earthquake could have been mislabeled as a military defeat, and the timeline of Homeric events would have been wrong. The same principle applies to other disaster types. A tsunami deposit looks like a thick lens of marine sand mixed with broken pottery and building stone, but so does a storm surge or a flood deposit. To distinguish them, archaeologists examine grain size, sorting, microfossils, erosion underneath, and debris orientation. Each clue eliminates one possible cause. It is a process of elimination that only works with enough independent evidence. Recognizing equifinality changes how we view the archaeological record. The evidence is rich with multiple meanings. Reading it correctly requires humility and patience. The best archaeologists do not claim certainty. They explain what the evidence suggests, how the alternatives were tested, and why this interpretation fits best for now. Equifinality does not lead to paralyzing doubt. It leads to sharper questions. Instead of asking what happened, you ask what could have happened, and then design your excavation to rule out possibilities one by one. A destruction layer becomes a puzzle to be dismantled, not a headline to be stamped. The mystery is not a flaw. It is the reason the science exists. Equifinality presents the challenge. Integration provides the answer. No single piece of evidence tells you what happened. But when you combine ash, bones, walls, and written accounts, the competing possibilities narrow. Only one coherent narrative remains. The most studied disaster in archaeological history demonstrates this method. The eruption of Mount Vesuvius in 79 AD is the example. Every type of evidence converges. The result is not a rough idea. It is a minute-by-minute timeline of an ancient catastrophe. The starting point is a written document. Pliny the Younger wrote 2 letters to the historian Tacitus. He described a cloud rising from the mountain that looked like an umbrella pine. Then came a rain of pumice and ash. Then a terrifying darkness. Finally, a cloud of gas and ash rolled down the mountain. This account gives a chronological framework, but it is only one perspective from about 30 kilometers away. The letters describe what the eruption looked like from a distance. They do not describe what happened in Pompeii itself. For that, we turn to the archaeological evidence. The ash layers around Pompeii are not a single uniform deposit. Tephrochronologists have identified several distinct layers. Each corresponds to a different phase of the eruption. The lowest layer is white pumice. It fell for roughly 1 hour and reached about 8 centimeters deep. Above that is a layer of gray pumice. It fell for about 7 hours. In some parts of the city, it accumulated to over 2 meters. Then there is a layer of sandy ash mixed with lapilli. It came from a partial column collapse during the night. Above that, the pyroclastic flow deposits appear. These are layers of hot gas and rock that surged across the landscape. They buried everything in a dense, cement-like mix of ash and debris. Each layer tells a different part of the story. The pumice fall caused roofs to collapse but was survivable if you stayed indoors or sheltered under something sturdy. The pyroclastic flows were lethal within seconds. Now we bring in the human remains. The Pompeii body casts are not random. Their positions are evidence of how people perished. Archaeologists mapped the location and posture of over 1,000 individuals. They recorded this information across the city grid. Those found within the pumice layers often have fractured bones. Their limbs are sometimes contorted, arms raised as if protecting themselves. They succumbed to roof collapse or falling debris, but the vast majority were found in the pyroclastic flow deposits above the pumice. Their bodies are curled in a defensive posture, hands near the face, knees drawn up. This is the position of asphyxiation and extreme heat. The bones show changes consistent with temperatures above 250 degrees Celsius. Shrinkage, collagen breakdown, skull fractures from internal steam pressure. This matches what the pyroclastic flow would have done. A cloud of gas at over 300 degrees carrying fine ash that clogged airways within seconds. The structural damage also fits the timeline. The walls that face southeast towards Vesuvius show the most severe damage. In the pumice fall, roofs collapsed under the weight of ash. The walls remained standing. In the pyroclastic flow, walls were knocked down. Often the damage indicates the direction of the surge. In some buildings, the walls tilt inward, away from the direction of the flow. The surge hit the facade and pushed debris inside. Archaeologists worked with structural engineers. They measured the amount of deformation in the walls of the House of the Faun and the House of the Vetii. The force of the flow was equivalent to a moderate earthquake, but the damage was only on the side facing the volcano. This pattern could not have been caused by an earthquake, which would shake the ground uniformly. It could only be caused by a directional blast. Now we integrate the chronology. Pliny the Younger tells us the eruption began around 1 in the afternoon on August 24th. The white pumice fall lasted about an hour. The gray pumice fall followed for about 7 hours through the afternoon and evening. Around midnight, the column partially collapsed. This sent the first pyroclastic flow down the mountain. It hit Herculaneum, burying people who had taken refuge in the boat sheds. Pompeii was not hit until the next morning, around 6 to 8 a.m. A major pyroclastic surge swept through the city. Several more surges followed over the next few hours. The position of the individuals confirms this timeline. Many people in Pompeii escaped during the first night, but about 1,500 remained. Some thought the worst was over. Others were trapped by the deep pumice. They perished when the pyroclastic surge hit. Computer modeling has reinforced this narrative. Volcanologists used the known volume of ash and pumice, the height of the eruption column, and the wind patterns reconstructed from the distribution of the fall deposits. They simulated the eruption in specialized software. The models produce exactly the sequence of events that the archaeological evidence suggests. The models also show that the first surge would have reached Pompeii in about 10 minutes from the time the column collapsed. It traveled at speeds of over 100 kilometers per hour. This matches the finding that many victims were still in their beds, wearing jewelry, clutching belongings. They had no warning. The integration of these 4 lines of evidence, written account, ash stratigraphy, skeletal remains, structural damage, and computer modeling results in a reconstruction that has stood for decades. It tells us not just that Vesuvius erupted and caused destruction. It tells the specific sequence. The white pumice fall was survivable if you stayed indoors. The gray pumice fall made escape difficult but not impossible. The pyroclastic surges that came the next morning were the real threat. The people who perished in Pompeii did not die in the first minutes of the eruption. They survived the night. They thought they were safe. Then the surge came. This reconstruction has concrete consequences. It tells us something about human behavior under threat. It also calibrates modern risk models for Vesuvius. The same sequence of pumice fall followed by pyroclastic surges. is exactly what a future eruption would produce. The timeline from the first sign of activity to the lethal flows is now known to be around 12 to 18 hours. That is the window for evacuation. The archaeological integration of Vesuvius does not just tell us about the past. It tells us how much time we would have if Vesuvius erupts again. The ash, the bones, the broken walls, and the eyewitness account are not four separate puzzles. They are four parts of one story. When you assemble them correctly, the past speaks with remarkable clarity. The integrated timeline from Vesuvius now informs modern risk planning. Civil protection agencies work with a 12 to 18-hour window from the first sign of unrest to pyroclastic surges. That figure came from combining Pliny's account, ash layers, victim positions, and wall damage. The same method is used for volcanoes worldwide. Tephrochronology, the study of volcanic ash layers, reconstructs eruption histories. Trenches around a volcano reveal each ash fall's unique chemical fingerprint. At Vesuvius, the record spans 10,000 years, showing major eruptions in 472, 1631, and 1944 as part of a recurring pattern. That recurrence interval helps estimate the next eruption's likely magnitude. For Santorini, the Minoan eruption's ash fell across the eastern Mediterranean and appears in lake sediments, peat bogs, and Greenland ice. Those deposits allowed geologists to build a recurrence interval for large Aegean eruptions. It is not precise, but it is better than no data. Earthquake hazard assessment benefits from archaeological destruction layers. Instrumental seismology covers only a century, too short for the rarest large events. At Kourion on Cyprus, buildings destroyed in 365 AD tilted and collapsed to the southeast, consistent with an earthquake on the Hellenic Arc. Radiocarbon dating from the destruction layer matched a known seismic crisis. By correlating such evidence from multiple sites, seismologists have extended the region's earthquake catalog back 2,000 years. Major earthquakes on the Hellenic Arc recur roughly every 800 years. The last was in 365 AD, placing the next in the coming centuries. That probability estimate informs building codes. Tsunami deposits leave distinctive overwash sand and marine shells. At ancient Olympia, a 6th century AD layer contained foraminifera from the open sea, indicating a wave at least 3 meters high. That evidence refined tsunami hazard models for the Western Peloponnese. On Crete, multiple tsunami layers from the Minoan eruption show waves over 10 meters. Those data now feed into the Mediterranean tsunami early warning system. Roman buildings that survived Vesuvius's earthquake show what resists seismic stress. Rubble-filled walls and heavy roofs performed better than timber frames. Engineers incorporated those lessons into building regulations for modern towns like Herculaneum and Thura del Greco. The distribution of bodies in Pompeii reveals effective shelter. Upper floors of well-built stone houses protected people from falling pumice. That informs modern shelter-in-place strategies. At Akrotiri on Thera, the absence of bodies suggests an organized evacuation. People had time to pack and leave, a positive example of community response to early warning. These data are integrated into geographic information systems that overlay ancient destruction layers with modern infrastructure. Italy's hazard maps for Vesuvius include evacuation zones based on the 79 AD timeline. Greek building codes in some coastal areas now account for tsunamis documented only through archaeological deposits. Ash, bones, and broken walls provide a longer baseline than written history. They reveal events erased from memory because survivors died or scattered. Without that baseline, we assume that the last 100 years represent the norm. With it, we see that the worst disaster in living memory may not be the worst possible. That awareness changes how we prepare, how we build, and how quickly we act when the ground shakes or the mountain shows signs of eruption. The past does not repeat itself exactly, but it gives us a range of possibilities. For any society that has never faced a major volcanic eruption or tsunami, that range is the only tool to avoid being caught by surprise. Yet even as we extract these records from ash, bones, and broken walls, the interpretations are far from settled. Some of the most famous ancient catastrophes remain deeply contested. Take the destruction of Sodom and Gomorrah. The biblical account describes fire raining from the sky and cities obliterated. For decades, archaeologists dismissed it as pure myth. They searched for conventional explanations like an earthquake or invasion. Then a team excavating Tall El Hammam in Jordan uncovered something unusual. Beneath a 1.5-meter layer of ash and rubble, they found pottery with surfaces melted into glass. Building materials had been vitrified at temperatures exceeding 2,000 degrees Celsius. The mineral composition was consistent with a high-energy airburst. The hypothesis, a meteor or comet exploded above the city, generating a shock wave and thermal pulse that destroyed everything. The evidence is striking but disputed. Critics argue that similar glassy deposits can result from lightning strikes or intentional firing. The connection to a specific biblical site also relies on contested textual identification. Was Tall El Hammam destroyed by an extraterrestrial event, or is the evidence being forced into a biblical narrative? The question remains open, and it has prompted the first systematic study of vitrified materials in archaeological context. A larger, more consequential debate surrounds the eruption of Thura and its role in the decline of Minoan civilization. The eruption was one of the largest in human history. It buried the settlement of Akrotiri under tens of meters of pumice and ash. But did it cause the end of Minoan Crete? The traditional view holds that the eruption generated a massive tsunami. It swept across the Aegean, devastating coastal settlements and tipping a flourishing society into irreversible decline. Tsunami deposits, including marine shells and pumice embedded in archaeological layers, have been found on the north coast of Crete. Yet the Minoan decline did not happen overnight. It unfolded over decades, perhaps centuries. Many inland palaces show no sign of tsunami damage. Some archaeologists argue the eruption was a blow but not a knockout. Minoan civilization may already have been weakening due to internal strife or drought. The debate hinges on chronology. If the eruption happened around 1600 BC, the gap before the final destruction of Minoan centers around 1450 BC is long. If it happened closer to 1500 BC, the timeline of cause and effect becomes tighter. That date discrepancy has been a battlefield for decades. Tree rings from bristlecone pines in California show a narrow growth anomaly around 1628 BC. Ice cores from Greenland record a volcanic sulfate spike that some researchers match to Thera. These point to an eruption in the late 17th century BC. But Egyptian historical chronology, based on king lists and astronomical records, places the eruption at around 1500 BC. Pottery from Akrotiri has been found in Egyptian contexts dated to that period. The gap is roughly a century and a half, with enormous implications. If the tree ring and ice core dates are correct, the entire Eastern Mediterranean chronology must be shifted earlier. This affects the dating of everything from the Hyksos period to the New Kingdom. Proponents of the high chronology argue that Egyptian dates are too rigid, relying on assumptions about scribal errors and the lengths of pharaohs' reigns. Proponents of the low chronology insist that the scientific dates are not uniquely tied to Thera. The sulfate spike could come from another volcano. The archaeological evidence for synchronisms, they say, is robust. Neither side has conceded. Studies of olive wood buried in Santorini's ash have produced radiocarbon dates around 1600 BC, but the calibration curve in that period includes plateaus that prevent narrowing the date to a single year. The debate remains active, driving refinements in radiocarbon calibration and forcing archaeologists to integrate tree ring and ice core data more rigorously than ever. Then there is the broader mystery of the Bronze Age collapse around 1200 BCE. Within a few decades, civilizations across the eastern Mediterranean unraveled. Palaces burned, trade networks collapsed, and writing systems disappeared. For decades, the culprits were assumed to be the Sea Peoples, raiders recorded in Egyptian inscriptions. But excavations have painted a more complicated picture. At sites like Ugarit in Syria, destruction layers show signs of both fire and abandonment, but not necessarily military attack. Some layers contain no arrowheads or siege debris, just ash and broken pottery, which could equally result from earthquakes. The pattern of destruction across the region is clustered but not simultaneous. It looks like a cascade of failures, one city after another. Drought has emerged as a leading hypothesis. Pollen cores from eastern Mediterranean lakes indicate a shift to aridity around 1200 BC. Stable isotope analyses of teeth from the period reveal increased signs of nutritional stress. Crop failures, famine, and social unrest could have made cities vulnerable to attack or internal collapse. But drought alone does not explain why some sites were violently destroyed while others were simply abandoned. The timing of the drought does not match perfectly with every destruction layer. Some researchers now view the Sea Peoples as a symptom rather than a cause. They were groups displaced by the same crises that brought down palatial economies. The Bronze Age collapse remains a case where multiple explanations compete. No single disaster theory has one consensus. This question has inspired collaborations between archaeologists, climatologists, and paleoecologists that would not have existed otherwise. What makes these controversies productive is that they drive the field forward. New technologies are gradually settling some disputes but also raising new ones. Ancient DNA can now identify pathogens in skeletal assemblages, but it cannot tell us how many people perished or why they were buried in such haste. High-resolution satellite imagery can reveal buried structures, but it cannot tell us if they were destroyed by earthquake or siege. The open questions remind us that disaster archaeology is not a closed book. Every reconstruction is provisional, a hypothesis waiting to be tested by the next excavation, the next core sample, the next fragment of ancient wood. That anticipation keeps the field alive, the knowledge that tomorrow a new piece of evidence could rewrite what we thought we knew about a catastrophe that happened 3,000 years ago. What will that evidence be, and which mystery will it finally solve? Three tools are transforming disaster archaeology: digital imaging, ancient DNA, and machine learning. Start with 3D scanning. A laser scanner or drone with photogrammetry can now capture every centimeter of a site in minutes, producing a model accurate to millimeters. That precision lets researchers map collapsed walls, shattered pottery, and each skeleton in relation to everything else. When the eruption of Vesuvius is recreated inside a computer, those models become raw data for simulations. Scientists can run the pyroclastic flow again and again, testing whether the damage matches the digital evidence. A Pompeii victim cast becomes a data point: the angle of the spine, position of the arms, fractures in the skull can all be measured and compared across thousands of victims. 3D scanning turns the site into a repeatable laboratory where reconstructions can be tested, refined, or discarded. Ancient DNA adds a biological dimension. Extracting usable DNA from bones interred for millennia has become routine. Researchers have sequenced DNA from Pompeii victims preserved in the ash. They identified a family group in the House of the Golden Bracelet, a mother, father, and children found close together. Isotopes in teeth revealed that some victims had migrated from the eastern Mediterranean, likely as slaves or traders. They also found tuberculosis, osteoporosis, and a genetic disorder that would have caused severe disability. The ash preserved not just the physical remains but the biological signatures of whole lives. DNA turns a plaster cast into a person with a family, a history, a medical record. Machine learning analyzes destruction patterns. Algorithms trained on hundreds of known events, earthquakes, fires, tsunamis, sieges, can recognize subtle signatures in broken walls and collapsed roofs. A model can scan a site and determine that the damage matches a magnitude 7.2 earthquake, not deliberate demolition. It works quickly, classifying a destruction layer in hours where a human archaeologist might need weeks. The machine does not replace judgment but provides a consistent, exhaustive second opinion. In a study of Roman coastal sites, a model identified tsunami damage that had previously been interpreted as earthquake collapse. The reconstruction changed, and so did the hazard assessment for the modern coastline. Isotope analysis reveals migration after disasters. By measuring strontium, oxygen, and lead ratios in teeth, archaeologists trace where a person grew up and where they lived later. After a disaster, survivors often fled or were relocated. Isotopes in post-disaster burial sites show the scale of that movement. For the Bronze Age collapse, isotope studies reveal that some populations moved hundreds of kilometers, merging with communities that had weathered the crisis. The disaster was not just a moment of loss but a long-term redistribution of people. Technology makes those demographic shifts visible. What all these tools share is a shift in perspective. The old question was what happened. The new question is to whom did it happen, and what did they carry with them? Technology has turned disaster archaeology from a science of layers and fragments into a science of individuals. A victim of Vesuvius is no longer an anonymous silhouette in plaster. She is a woman who walked the streets of Pompeii with brittle bones from a genetic mutation, who raised a child with a different father who may have come from a distant land. The ash that engulfed her preserved that story, and now we have the tools to read it. That changed perspective also forces humility. The more data we collect, the more we realize how much context we are missing. A single DNA sample gives ancestry but cannot explain why that person was in Pompeii that day. A 3D model shows exactly how a wall fell but cannot tell if someone tried to hold it up. Technology opens windows but does not remove the mystery. It simply makes the mystery more precise, and that precision keeps disaster archaeologists pressing forward, because each new tool reveals not only answers but deeper, more human questions. But that precision brings its own weight. When you look at a Pompeii victim reconstructed from DNA, you see a life, a family, a future erased in hours. Disaster archaeology stops being technical and becomes something harder to define. There is a quiet frontier in this field, one not found in journal papers or tephra layers. It is the emotional archaeology of disasters, the way archaeologists wrestle with the human tragedy in their evidence. Archaeologists excavating mass burial pits do not simply record bone positions and take soil samples. They touch remains untouched since that person's final breath. They handle the remains of a child from a plague trench, one of millions lost to a pandemic that devastated half of Europe. They clear ash from a woman's skull in Herculaneum, knowing her final moment was superheated gas. Doing that work without being overwhelmed requires a unique focus. Many archaeologists describe it as a form of reverence, a silent acknowledgement that they are the last witnesses to lives that ended in terror. The ethical questions are not simple. Take the plaster casts of Pompeii. They are iconic, but they are also the preserved forms of people who once lived. The cavities Vesuvius left in the ash capture every detail. Pouring plaster creates a perfect replica of the person at the moment they perished. Is that replica a scientific artifact or the physical record of a life? Museums have debated this for decades. Some visitors come to learn, others to gawk. In recent years, several museums have begun covering the more intimate casts with cloth, arguing that displaying a person's final posture reduces humanity to spectacle. The line between knowledge and voyeurism is thin. The same tension arises with mass burial sites. At the Royal Mint site in London, archaeologists excavated skeleton after skeleton from the Black Death Trench with extraordinary care, documenting bone positions, taking DNA samples, building a demographic profile. But afterward they had to decide how to treat the remains. Should they be reinterred with ceremony despite anonymity, held in storage for future study? In the end, the bones were reinterred in consecrated ground, acknowledging them as people, not just data points. That choice reflects a broader understanding. Disaster reconstruction is not just scientific but moral. Sensationalism is a constant risk. Media coverage often uses the most visceral images, contorted postures, open mouths, rows of skulls. It sells, but it distorts. Archaeologists fight that by emphasizing context and cause over horror, giving victims a voice without turning them into morbid objects. Language matters. When a site report describes a Herculaneum victim's position as a defensive fetal curl rather than a panic posture, it shifts interpretation toward empathy instead of shock. And empathy sharpens the science. An archaeologist who sees the people in a boat shed as a family group, not random individuals, will look for genetic relationships, shared diets, social bonds that explain why they perished together. Emotional work becomes a research tool, forcing better questions. There is also the question of who tells these stories. Many excavated sites belong to communities still living nearby, whose ancestors may have been victims. The Thura tsunami deposits on Crete touch on modern Greek identity. Plague burials in London resonate with a city that remembers its own epidemics. Archaeologists increasingly work with local descendants, sharing not just data but the weight of memory. It acknowledges that the past is still alive, that these disasters did not end when the last survivor passed. A destruction layer is not the end of the story. Above it there is usually another layer, rebuilding debris, new foundations, sometimes a complete change in a city layout. Archaeologists call this the post-destruction horizon. In most cases, ancient people did not simply vanish. They adapted. They rebuilt on the same ground, often within a generation, sometimes using the same stones. The Temple of Jupiter in Pompeii was already being reconstructed when Vesuvius erupted again. That continuity is one of the most consistent findings across dozens of ancient disaster sites. But continuity does not mean a return to normal. The social and economic aftermath leaves its own signatures. One of the clearest is coin hoards. When a disaster threatens, people often bury their valuables, planning to recover them later. If they never return, those hoards remain, a silent inventory of what people valued most. Archaeologists have found hoards from the eruption of Vesuvius, the destruction of Carthage, the collapse of Roman towns in Britannia. The patterns tell us about the shock, the depth of burial, the variety of coins, the presence of jewelry or tools. A hoard with many gold coins suggests wealth concentrated in a few hands right before the end. A hoard with a mix of everyday items suggests a hurried evacuation. Demographically, the aftermath can be read in skeletal remains. Communal burial sites from disease or volcanic events often contain an overrepresentation of the very young and very old, the most vulnerable. The recovery period shows a different signature, a baby boom as surviving populations attempt to replenish numbers. Skeletal studies in post-Vesuvius cemeteries in the Naples region indicate a demographic rebound within about 20 years. The recovery was not just biological but cultural. New pottery styles appear, new building techniques are adopted, and sometimes new religious practices emerge as communities reinterpret the disaster as a divine message. Perhaps the most studied example of aftermath is the Minoan civilization after the eruption of Thura around 1600 BCE. For decades, scholars argued that the eruption destroyed the Minoans, that the volcanic cataclysm so weakened their economy and society that they fell to the invading Mycenaeans. Archaeological evidence from the last 30 years paints a more complex picture. Excavations on Crete show that many palatial centers were not suddenly abandoned. Instead, there is evidence of rebuilding, reorganization, and even expansion at sites like Knossos. The famous frescoes do not suddenly vanish, they evolve. The interruption of trade networks is visible in the absence of certain imported goods for a few decades. But by the late Bronze Age, Minoan artisans were again exporting luxury goods across the eastern Mediterranean. The real change was not destruction but transformation. The Minoan economy shifted away from centralized palace administration toward a more decentralized network of smaller settlements. The eruption did not destroy the civilization. It accelerated changes that were already underway. This is a key insight for disaster archaeology. The aftermath is not simply a period of loss but a period of choice. Communities could abandon the site entirely, as happened at Akrotiri itself, which was never reoccupied after the eruption, or they could adapt, as happened across Crete. The archaeological evidence, the absence of new foundations, the presence of imported goods, the shift in building materials, records those choices clearly. One compelling indicator of adaptation is construction technique. After an earthquake, archaeologists frequently find that the next building phase includes tie rods, stone foundations, or timber lacing, engineering solutions learned from the disaster. In Pompeii, the buildings constructed in the decades before the final eruption show evidence of seismic retrofitting: arches, buttresses, and reinforced doorways. These were not random improvements. They were informed by the tremors that had been shaking the town for years. The residents knew they lived on shaky ground and tried to make their homes safer. The demographic data from post-disaster cemeteries also reveals a pattern of resilience. When a community survives a catastrophic event, the age structure of those who died often shifts. There are fewer elderly victims in the immediate aftermath because the most vulnerable have already died. But the next generation shows a higher number of adults in their prime, people who either moved in from outside or survived and then had children. Stable isotope analysis of teeth from post-Thera skeletons on Crete reveals that some individuals were not local. They had migrated from the Cyclades, perhaps displaced by the eruption itself. The disaster created a diaspora, and archaeology can trace where they resettled. Economic disruption is visible in the presence or absence of trade goods. For about 50 years after Thera, Minoan pottery from the period is scarce in the Levant, but it does not disappear entirely. Within a century, Minoan goods are again common along the coasts of Anatolia and Egypt. This is not a collapse, it is a readjustment. The eruption knocked out a major trade hub, but the networks rerouted. It took time, but the Minoan economy did not end. It changed. What this means for disaster archaeology is that the aftermath is not a single moment. It is a process that can last decades or centuries. The archaeological record gives snapshots of that process: the collapse layer, the abandonment horizon, the rebuilding phase, the new pottery style, the changed diet. Each layer is a decision point. Each broken wall is a lesson learned or ignored. The concrete discovery here is that ancient disasters rarely end civilizations. They transform them. The transformation is not always decline. Sometimes disaster creates opportunities for innovation, for new alliances, for new ways of building and living. The evidence from Crete shows that after Thera, the Minoans did not disappear. They adapted. They became something different, still recognizably Minoan but changed by the trauma. But not all civilizations adapted so successfully. Some did collapse, or at least their archaeological record shows a dramatic break. The question disaster archaeologists ask is whether a single catastrophic event caused that collapse, or whether the disaster was merely the final blow to a system already crumbling from accumulated stresses. This is where the evidence of ash, bones, and broken walls meets the largest debates in prehistory. Consider the Mycenaean civilization of late Bronze Age Greece. Around 1200 BCE, the great palace centers burned and were abandoned. For decades, the standard explanation was an invasion by the mysterious sea peoples, or perhaps a wave of earthquakes. But when archaeologists looked more closely at the destruction layers, the pattern was not uniform. At Mycenae itself, the palace shows clear evidence of fire. At Tiryns, the walls are tilted in ways that suggest seismic shaking. At Pylos, the linear B tablets mention preparations for a naval threat, yet there is no battle damage. The evidence is contradictory. It points not to a single disaster but to a century of accumulating problems. Drought leaves its signature in lake sediments and pollen cores across the eastern Mediterranean. Those records show reduced crop yields. Trade networks faltered, visible in the sudden decline of imported goods like ivory and tin. The palaces had become brittle. They depended on centralized redistribution of food. When the system strained, it shattered. The fires and earthquakes were not the cause. They were the shocks that broke an already cracked structure. The same debate plays out in the Maya lowlands. The classic Maya collapse around 900 CE saw a population decline of up to 90% in some regions. Early theories pointed to a single catastrophic drought, but the archaeology reveals a more complex story. Dendrochronology from Central America shows a series of severe droughts, not one. Lake sediment cores indicate deforestation and soil erosion. Those changes made the landscape less resilient to dry periods. Excavations at sites like Copan show that elite monuments and royal tombs become smaller and less frequent decades before the final abandonment. The collapse was a process, not an event. The droughts were disasters, but they struck a civilization already pushing the limits of its environment. Then there is the case that brings these questions into sharp focus. The climate anomaly of 536 CE. Ice cores from Greenland and Antarctica preserve a volcanic aerosol spike. It caused global temperatures to drop for years. Written records from Byzantium, Ireland, and China describe a dim sun, failed harvests, and famine. But does this disaster have an archaeological signature? In Scandinavia, many villages were abandoned around that time. Precious metal hoards were deposited, suggesting crisis. In the Maya world, the same period coincides with the abandonment of Teotihuacan influence in the highlands. Yet linking the 536 event directly to those local collapses is difficult. The archaeological layers are not precise enough to prove causality. What the evidence does show is that a known climate disaster created conditions of stress. Different societies dealt with those conditions in different ways. Some collapsed, some adapted, some transformed. This is where disaster archaeology must guard against a tempting trap. It is easy to see a destruction layer, a period of abandonment, and a changed material culture. Easy to conclude that the disaster destroyed a civilization. But the leap from destruction to collapse is rarely that simple. Societies are not static. They can recover, relocate, or reinvent themselves. The Minoans did not disappear after Thera. They reorganized. The Mycenaean palaces collapsed, but the Greek population did not vanish. The subsequent Dark Age saw a shift to smaller villages. New mortuary practices emerged. Eventually, the city-state rose. The collapse of a political system is not the same as the collapse of a people, so the bigger picture forces an open question. When we look at the great collapses of history, the Bronze Age collapse, the Maya decline, the fall of the Western Roman Empire, can we attribute them to any one disaster? Or were they the cumulative result of multiple stresses, with disasters acting as triggers that accelerated inevitable change? The archaeological evidence often points to the latter. Yet every case is different. The science continues to refine its dating methods and its proxy data. Researchers try to match tree rings, ice cores, and ash layers to the archaeological destruction horizons. With each refinement, the simple story of a single catastrophic collapse becomes more elusive. It is replaced by a more human narrative of choices made under pressure, of resilience, of failure, of adaptation, of change that is neither total nor final. We began this journey sifting through ash layers, reading fractures in human bones, and measuring the tilt of fallen walls. We watched archaeologists work like detectives, comparing evidence from Pompeii and Herculaneum, from Thura and the plague pits of London. We saw how a single broken wall can mean an earthquake, a siege, or a fire, and how a communal burial site can tell us about disease, war, or famine. The method is painstaking, the interpretations provisional, and in the end, the disasters themselves are never just about destruction. They are about what happened before, what happened after, and what the survivors chose to do. The central promise of this investigation was to understand how archaeologists reconstruct ancient disasters from ash, bones, and broken walls. But that reconstruction is never a simple answer. It is a conversation across time where the evidence speaks in fragments, and the archaeologist must listen with patience and humility. The ash that covered Pompeii also preserved it. The bones of Herculaneum reveal the exact moment of thermal shock. The broken walls of Curian record the direction of an earthquake wave. Each piece of evidence is a witness. And the archaeologist's job is to assemble those witnesses into a coherent story, knowing full well that some voices will remain silent, some details lost forever. That brings us to the insight that matters most. Archaeology does not give us certainty about the past. It never can. But it does give us a way to hear the voices of those whose lives were cut short without a record. By reading the ash, the bones, and the broken walls, we do more than reconstruct disasters. We recognize that our own societies are just as vulnerable. The same forces that covered Pompeii still threaten Naples. The same tsunami that struck ancient Olympia could hit any coastal city. The same plague that devastated medieval Europe has not been completely eradicated. The past holds warnings, and we ignore them at our peril, but the past also holds a quieter message. It shows us that people survived, they rebuilt, they adapted. The Minoans after Thera, the Romans after the fire, the Londoners after the plague. The evidence of resilience is woven into the same ash, bones, and walls that document the disaster. So the reconstruction is never just about loss. It is about life continuing, about the human capacity to endure, and about the choice to remember. That resilience was not a single moment but a process of decisions made under pressure, of failure and adaptation, of change that is neither total nor final. Each disaster left a mark but also a path forward. The same layers that record destruction also record renewal. And in that interplay lies the deepest lesson for modern societies. Our cities are built on the same ground that experienced past cataclysms. Our infrastructure faces the same seismic faults, the same storm paths, the same biological threats. When archaeologists piece together an ancient earthquake or eruption, they are not just satisfying curiosity. They are building a long-term record of risk, one that can inform how we prepare for the next event. The science continues to refine its dating methods and proxy data, matching tree rings, ice cores, and ash layers to archaeological destruction horizons. With each refinement, the simple story of a single catastrophic collapse becomes more elusive. It is replaced by a more human narrative of choices made under pressure, of resilience, of failure, of adaptation, of change that is neither total nor final. We are left not with certainty, but with a deeper understanding of how societies face extremes. That understanding is the true value of this work. It forces us to ask how we would respond under similar strain. And it reminds us that the past is not a closed book. It is a conversation still in progress. Now I want to hear from you. Which archaeological disaster reconstruction do you find most compelling, Pompeii, Thura, or the plague pits? Let us know in the comments. If you enjoy history's unsolved mysteries and the science that uncovers them, subscribe to join us on the next investigation. The past is still speaking. We just have to know how to listen.